Hello.
Hi, everyone. Hope you can hear me.
Yes, I can hear.
Hi, Lance. How you doing?
Good, good. How are you, Asuka?
I am well. So guys, you already know the drill. If you can open your camera, please, let's get to know each other. It's gonna be a long ride. Uh, so if you can open your camera, please do so. Yeah, maybe we can hang around for like 5 minutes and then get started. Okay.
Cool.
In the process, just gear up for opening your camera. Jonathan, Naomi, please. Yeah.
Also, guys, we are not judging the quality of the camera. You are not your camera.
Greetings, you are excused, and thank you for being the one person that has given us a valid excuse. Is it an excuse or a reason? But next time, I'm on to you, greetings. Today you can pass. So 1 more minute. Yeah. So I think it's a good time to start, right? Yeah. So we'll get started so we can keep time. Thank you so much, guys, for joining, for making time to join us today. And this is our first session. As we mentioned, this week we'll be covering blockchain fundamentals. So we have 2 more sessions for the week. And today we have a very special instructor to Web3 Clubs, a friend of Web3 Clubs, Lance Davis. He picked a very interesting, and I'm very excited to see how the session is curated for today. I think we're going to do a lecture for 1 hour and then 30 minutes. We can ask the questions, but I'm not sure if they're free to interrupt you, Lance. What if it gets too hectic? Can we unmute ourselves or is it strictly 1 hour?
It should be a discussion if possible. We'll have slides to guide the conversation, but if you want to talk back, if you want to ask questions, go ahead. Feel free to interrupt.
Awesome. So the reason I had to make that clear is because I know we have complete beginners to blockchain and we don't want you to get scared off. It's a free space to learn, ask your questions. Maybe things will get easier next week. More people are familiar with AI compared to blockchain, but this is gonna be intense. And we hope you enjoy the session. Yeah, Lance, you can take it away.
Cool, cool. Thanks, Washuka. And really great to meet y'all. Really, really happy to have met Cohort 10. I appreciate y'all having me tonight. So I'm Lance. I'm uh, a 2-year long friend of Web3 clubs. Actually, my first time in Kenya was in 2024, and it was just 2C Web3 clubs. I'm originally from Chicago, Illinois. I've been a blockchain engineer for the past 5 years, coming on 6 years. So overall, just have been deeply involved in the crypto and Web3 space. Also, I've done a little bit of work in the AI industry, but before I got into crypto. But what I'm doing right now is I have a startup called Sereel, which is a company that I started along with someone that I met through the Web3 Clubs community. We provide institutional custody and tokenization for asset managers and banks. And essentially, the important takeaway that I really want for this presentation tonight is for you to know that blockchain is not a finished concept and Web3 is not a complete project, right? Most of these technologies that we're speaking of have been in the process of being created over the past few decades. And there are new primitives and new concepts that are still being developed today. And just because you're learning for the first time today, it doesn't mean that in the next, 3 to 5 years, you won't be contributing to the state of the art. So with that, I'll get started with my presentation. Uh-oh. Oh, I need to approve Zoom to do screen sharing. So I'll leave and then join right back.
Ochi, I've tried begging people to open their camera. Maybe they will listen to, I don't know, you.
I don't know. I just know God is watching them. That's all I know.
Yeah, that's
Also,
a good guilt trip.
yeah.
Yeah.
Also, please take note. We are taking attendance. Um, yeah, we're taking attendance. Let me just say that, and 75% attendance is what we're going for. So just I hate to be the principal, but yeah, it is what it is. That's just how it is. Yeah, Lance, I see your back.
Yeah, sorry about that. Okay, cool. So can you all see the blockchain Canon screen, the presentation? All right, cool. I see the nods. All right, let's get into it, y'all. Remember, feel free to interrupt, feel free to ask questions. This is an open discussion, if anything, yeah? So we'll start. Let me just start by removing this. Uh, can you all see these cameras on the side? The can you all see the full screen? Okay, you
Yeah,
can't see the
yeah,
full
yeah,
present.
yeah, yeah,
You can see the full presentation.
yeah. I
Okay,
believe so.
nothing's
Yeah.
blocking it.
No.
All right, perfect, perfect. So we live in a world of the internet where basically nobody trusts each other. And even before AI, nobody trusted each other. There's no police, no bank, there isn't a central server, there's not like a government for the internet, right? And this has been a problem since the inception of the internet. When Tim Berners-Lee created the first HTTP hypertext transfer uh, protocol, there was no way to transfer value or transfer legitimacy on the internet. Everything was based on trusting what you see and not really being able to verify it. So the two primitives that made blockchain even possible in the first place were digital signatures and hash functions. So we'll go into these in the next few slides, but essentially digital signatures, they prove authorization without necessarily revealing underlying information. And hash functions, they prove the integrity of information by providing something like a fixed fingerprint. So it started in 1976 with the Diffie-Hellman algorithm. It was the first example of how a mathematical concept called the discrete log problem can be used to securely communicate between or to establish secure communication between two parties in a system that where trust is not guaranteed, right? If I wanted to tell you a secret, through your ear, I would just cover your ear and then tell you. But over the internet, where everyone can see traffic, you need some type of mathematical certainty that these secrets won't be exposed. And essentially, how it was made was you take this mathematical concept called a finite field. You encode data into this finite field, and then you give everyone on the internet a secret private key that only they know. And this private key is used to do a certain mathematical operation on data so that anyone with your public key, right, they can use it to prove that you generated that data, or at least that you signed that data. So everyone on this Zoom call right now, you currently have a private key in the form of a VoIP certificate, which is a voice over internet protocol. And you have a public key, which is what the Zoom software is actually using to determine who you are on this call. So this is literally how the internet works today. And it's the same concepts that have been applied to blockchain. In particular, elliptic curve cryptography was a major breakthrough because it essentially is able to achieve massive feats in security with low memory space, right? So as you see at the bottom, RSA is another type of digital signature. In order to get the same amount of security for an RSA signature, let's say you have 3072 bits, which is a huge amount of memory for something, transferring over the internet, right? Because every time you send a byte, which is 8 bits, that is actually traffic that is coming out of your computer onto the internet to all of the other recipients. So, for example, if this Zoom call was using this third 3072 bit structure, you all probably wouldn't even be able to hear me that well because of all of the traffic. So, elliptic curves are these more complex mathematical structures that make it so that uh, increase like a lot of complexity can be compressed down to a smaller amount of bits. And let me know if you all want me to go deeper on elliptic curves. The math is really elegant, but it would take a it would take a long time. So, like we had said, digital signatures with elliptic curves. This is really how the internet works today. So the original ECDSA, that was the classic elliptic curve signature, but today we have Schnorr and EDDSA signatures, which are used on the internet and across blockchains. These essentially, if you change one byte in a signature, then the entire signature fails, right? So if I sign some data, like let's say I'm sending out an email, right? And I use my ECDSA signature to sign that email. If it gets corrupted in transit and one bit is flipped, then that means that the recipient to the email really can't even verify that that email came from me, and that email will probably bounce. So, when we say the entire internet runs on these signatures, it really does. And then what we also had mentioned are hash functions, where you take a certain string, you run it through an algorithm. It's there are lots of different names for the algorithms that can be used for hash structures. Like some are called Feisel structures, some are called sponge structures. There are different ways to create hashing algorithms. The ones that are popular for blockchain typically are much smaller and efficient, like SHA-3. But essentially, it maps any type of string to a constant 256-bit output. So if you like this example at the bottom, you have the word hello. It maps to a certain hash, but then you change the O to a P, and then it maps to a completely different hash. So these are kind of used for kind of fingerprinting, because now every single string that is out there in the universe has a unique 256-bit value that it can map to. And the reason why is because 256 bits, if you do the math on it, it's able to encode more values than the number of atoms in the universe. So there's no way that we can overrun this the amount of outputs here. You can do basically every text output with the entire alphabet, all of the numbers, all of the symbols. It doesn't matter. It's going to be able to come up with a unique, consistent output. So this is where we get to SHA-3 and Keccak. So SHA-3 is the most recent cutting edge hashing algorithm. There were some recent hashing algorithms that are quantum resistant called Falcon, but these were the ones that were around when Ethereum was created, which is what we'll be talking about in this presentation. Bitcoin actually predates SHA-3 though. So Bitcoin actually used SHA-256, which is a slightly less secure version of the hashing algorithm. But because Bitcoin has its sophisticated consensus model, the security of the hash actually doesn't quite matter as long as it's secure enough. And then one of the most important structures, mind you, all of these different primitives, right? The hash functions, the signatures, all of these were created by different researchers over the past, since the 80s, right? So it's not like a lot of them had these blockchain use cases in mind. A lot of them were really looking to solve problems that were purely math at the time. And then computer scientists then took that math and then applied it to real world use cases. We'll see more of that with a lot of the programmable cryptography we'll talk about at the end. Any questions? Any questions so far before we get into Merkle trees? I know we're going super fast.
Yeah, yeah. What is a blockchain?
Oh, a blockchain is a database, essentially. that is verifiable amongst multiple members in a network. Um, that's a very simple way of putting what is a blockchain. I actually don't have that definition in this presentation. It's good to know. But you can think of it in a way where if I have information stored on a blockchain, I know that it is not going to be corrupted for the foreseeable future.
So what brought about the need for blockchains and yeah,
So that
and
is
also
back to that.
and also give examples in real life where blockchain is like useful use cases or potential use cases, even if they're not been implemented yet.
Yeah, definitely, definitely. So that gets back to that governing force on the internet problem. If I'm someone on the internet and I can post anything from my server, any website, how do I trust the information on that website, especially if I'm trusting it with my own information? So the most basic example for the need of a blockchain is for an internet-based currency, right? So we had digital currencies that were run via bank servers, but those servers are run by the banks. So if I am a customer of one bank and I see my digital account, that doesn't necessarily mean that I can take that value and use it on other places of the internet, especially in different, for example, different countries, right? So when it comes to creating a ledger, which is kind of what a bank has, what a bank maintains on their server, but a ledger where the entire internet knows is up to date and faultless was an innovation that was not possible on the internet before blockchain, right? We've had the internet for so many years, but we weren't able to send money instantly from country to country because we didn't have blockchains. Because if I am a bank in Kenya and I want to send money to a bank in the US, the servers that I'm running in Kenya have no way to trust the servers that are running at the bank in the US and vice versa, right? So now there's this structure on the internet where information can be trusted throughout the entire internet, regardless of, who wants to run the server or not. It's just a protocol that ensures the information is secure. That's cool. Good, good.
Yeah. So I'm just trying to even sum it up for the people. So the blockchain is a collection of networks, protocols, rules that basically ensure that the internet is, I would say, verifiable, uh, trustless. So you can basically believe that the state of a database and the internet is essentially truly true. And also at the core of the blockchain is this idea around decentralization, which probably Lance will touch on at some point or even now. Yeah,
Yeah. We'll get into decentralization when we hit consensus networks.
yeah.
So yeah, this primitive, the Merkle tree, is a really important one to know because they're used everywhere in blockchain, crypto, ZK, you name it, Merkle trees are used. And the reason why is because they're really good at compressing data. And compressing data is not just for example, like Reed Solomon encoding or um base 64 encoding. It's compressing secure data. So a Merkle tree consists of a root, the Merkle root, and then all of its children, which are attestations to some type of information, right? So if I hash, right, those hashing algorithms that we talked about, let's say I take the hash of the word hello, and then I take the hash of the word this hell p, right? But then what happens if I combine those hashes and then hash it again? It is not, it's no longer a for a 512-bit output, it is now a 256-bit output again, even though we combine the two outputs, right? And then we do it again with two more hash results, and then we combine them into one 256-bit output again. And then we keep doing that over and over again until we have one Merkle root. The concept of Merkle trees is not intuitive, so let me know if this makes sense. So you're taking information, let's say two pieces of information, you're hashing those two pieces of information, you're putting them together. Now you have a 512-bit output. And then you hash that 512-bit output to create a 256-bit output. And then you do that for another subtree. And what I mean by subtree is another two pieces of information hashed together and then the output hashed. And then you keep doing that until you just have one Merkle root that is a 256-bit value. And that Merkle root can be used to attest to all of the underlying information, right? Let's say I have the original information just for this TX1, for this transaction one. I can show you that information and say, hey, my transaction is included in the blockchain. And then you hash that, you combine it with the hash of transaction two, and then you get this capital H. And then you combine that with the other capital H, and then you get the Merkle root. So you know that your data was actually in the original Merkle tree when that Merkle root was created. So this concept is going to be used. There are lots of different ways to um, optimize Merkle trees. Like, for example, now in Ethereum, they don't use Merkle trees anymore. It's called Virgle trees, where there are vectors of hashes at each layer, but the concept is still the same. You are compressing information in a way that all you need to put on chain is this one little 256-bit value to attest to a lot of different transactions so that you keep as much information off the blockchain as possible. And we'll get into why you would want to do that later. The concept makes sense though? Okay, oh my goodness. We are at 27. I need to hurry up. So we have the Byzantine generals problem. So we've covered the cryptography background, right? Now we're going to get into consensus. So the main problem on the internet is that nobody trusts each other. This is the main concept. Because nobody trusts each other, how can we all reach an agreement? If one person is incentivized to basically mess everybody else up, they will do that because they don't care about anybody else on the internet, right? How do we all come up with the decision on the internet where everyone doesn't trust each other, but everyone shares the same incentive, right? And we'll answer this in a little bit. Um, Paxos was one of the first consensus algorithms. Followed now look at this. This was 1989. This technology has been in development for a very long time. You have PBFT, which essentially we it took us time to get to the point where we're able to actually have a consensus algorithm that fits for the internet today, where Paxos had assumed that people would their computers would crash, right? It's not their fault. They're not necessarily being malicious, but that's not true because on the internet, people are malicious. People are evil. And then PBFT, it did tolerate malice, but you needed a fixed amount of membership. It wasn't as expansive as the internet, where anybody can join the internet, right? As long as they have the fiber optic cables and stuff. So we needed a consensus algorithm that had open membership lists, meaning anyone on the internet can join, and then also where everyone could be malicious, everyone could be against each other, and we still come up with a common decision. So over time, they got more sophisticated. So BitTorrent, for example, was a way to share information over a peer-to-peer network. And these peer-to-peer networks, they use these things called hash tables, which would essentially hash data, and everyone would share the same uh, 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 registry of hashes, and these hashes would be used to attest to the information that is being shared on BitTorrent. So if I were to send you something on BitTorrent, you'd be able to check your own hash table against the information that I'm sending you. Because if you hash that information, then that hash should be on the list that is allowed on the BitTorrent network. All right. So this is where 2008 comes around, and we finally get to Nakamoto consensus, which is proof of work, right? So if nobody else trusts each other, how do we make it so that we can mathematically enable the trust between two different parties where everyone is malicious against each other, right? On the internet where nobody trusts each other, how can we form a source of truth? And it's done in proof of work with a hash puzzle. And this puzzle essentially says I am going to take the same piece of information or like random bits of information, and I'm going to keep hashing this information over and over and over again until a certain amount of the first bits of this 256-bit output are all zeros. And everyone is going to agree the amount of zeros you have to achieve in order to win this puzzle, right? And then when the puzzle is won, that's when the individual is able to add a block to the blockchain. So the puzzle essentially acts as a mediator between everyone else in the network. Because essentially, I can say, I have this piece of information that hashes to the right value that everybody else is looking for. And everybody else can take that information and hash it themselves and prove that it is correct. And that correctness is what creates the trust for everyone in the Bitcoin network to trust the state of the blockchain. And what we mean by adding blocks to the blockchain, it's just more information. So what OT had asked earlier is like, what is the point of the blockchain? The point of the blockchain is to maintain a ledger of record, right? Who owns what? That is what the blockchain is doing. Every transaction adds to that list and it changes the list a little bit, right? At some point, I owned, XYZ. At some point, somebody else owned XYZ. I sent them assets, and then now the ledger has changed. Who determines the validity of the ledger as it's changing? This is where proof of work comes in. So speaking of transactions, the Bitcoin model, it runs on the unspent transaction output model, or in other words, the UTXO model. And this UTXO model basically separates all of the blockchain's assets into spent and unspent, right? So whatever I have in my wallet, that is unspent currency. Whatever I have sent to you or anybody else, it is marked as spent. And now it is your unspent balance. The goal of the UTXO model is to make it so that people cannot spend the same currency twice. Once you have currency marked as spent and it is settled on the blockchain, you cannot mark it as unspent. You can't go in reverse, right? The thing about the UTXO model though is that it's hard to program. And what we mean by that is that if I'm dividing all of the assets on the blockchain between spent and unspent, it means that I don't really have fluidity, right? What if there is another party that isn't necessarily spending or saving or unspending the currency, right? What if it's supposed to be like an escrow of sorts? And this is where we get into smart contracts later. But the UTXO model, it's essentially the basis of Bitcoin's what we can call accounting format. So as you can see, um, all of these technologies, SecP256K1, the hashing, SHA-256 hash, the proof of work algorithm for consensus networks, peer-to-peer communication, UTXO, all of these concepts came together in the Bitcoin paper to create what we know today as Bitcoin, right? So then that gets us to the account model. So then after there was some time where Bitcoin had existed, there was uh, some argument in the Bitcoin community around the programmability of the UTXO model. And this is where we came, where we got the account model. This was in the Ethereum yellow paper that Vitalik Buterin and Gavin Wood released in 2014. So essentially, the account model works a lot more intuitively as you would think, right? It's one address and they own a certain encoded balance, right? They don't have these two balances that says, hey, I have this unspent amount and this spent amount. It's very simple. This account has this balance, period. And this made it so that the blockchain is more programmable. Right now, Bitcoin, there's a limit to how programmable it can be, but the Ethereum blockchain is essentially computer, the world computer blockchain, where now we're not just accounting for value, we're not accounting for uh, how many coins people own. Now we actually have a Turing complete virtual machine, which is basically a fancy way of saying a computer whose state the consensus network agrees on. And what I mean by that is a computer itself, right? Let's say we were to stop time right now, everyone's computer would have a specific state, right? All of you all would have Zoom open. All of you all would maybe have a browser on the side. Maybe you all have like different applications on your computer. That is the current state of your computer. And if you close Zoom, if you send a message in Telegram, if you do anything on your computer, it changes the state of the computer. The same thing works on Ethereum, where the state itself determines who owns what and what smart contracts are even on the blockchain to facilitate that transfer of ownership. Okay, before we get into ZK proofs, is this following the difference between Bitcoin, how we got from Bitcoin to Ethereum, why we needed to go from Bitcoin to Ethereum?
Um, I think I can see some guys saying yes.
Mm.
So I think maybe ZK is, I don't know how many guys know what a smart contract is.
Okay, you
Yeah,
can go into that.
because you're going into ZK and you haven't touched what a smart contract is. Maybe you
Mm.
can get into what makes Ethereum the world's computer, I guess, and the architecture of blockchains like Ethereum and
Mm.
what makes them different. So what's the difference between because guys are just hearing maybe some of them. No, I'm sure not all of them, but some may be hearing blockchain for the first time and they're putting it together, and then you're talking about a programmable internet, programmable computer. Maybe you can explain what that means and and
Yeah, yeah,
and the foundations of that.
100%. Right. Okay. So so Bitcoin is Bitcoin. On the Bitcoin network, the only thing that the Bitcoin network does, right, is it maintains a ledger of who owns how much Bitcoin. And it does this by labeling every coin as spent or unspent by this address, by a certain address, right? This is a clunky way, but it works, but it's a clunky way of accounting for who owns what. Because let's say I were to create a Bitcoin wallet, and this Bitcoin wallet had a simple switch in it, and this switch determined, well, maybe this switch was triggered by some type of, we wanted it to be triggered by some type of external factor, right? So if this person guesses the number right, then they should win the Bitcoin in that wallet. If not, then they shouldn't win the Bitcoin, right? Simple. Does the number match or no? That's extremely difficult to do in Bitcoin. It's possible to do in Bitcoin. You're able to create so there Bitcoin has this feature. It's how they're able to build like the virtual machine on top of Bitcoin, where you're able to have some clauses for a UTXO transaction. And one of those clauses could be something where you encode a certain value into it, but it requires you to be a Bitcoin engineer. You need to know how to um, actually program the Bitcoin in your wallet. And then also, it's just extremely inconvenient. So in order to make a program like this, where I have where I can put a certain amount of tokens inside of a wallet and then only enable people to win what is inside that wallet if they guess a number correctly, it's much better done the way we've been doing it for years, which is with programming languages, right? So that's the reason why we have programming languages like Python, Rust, C++. It's so that we can easily, a human being can easily embed this type of logic into a computer program. What Ethereum, sorry, y'all, I just ate. Um, what Ethereum enables you to do is to write a script in Solidity or Viper and execute logic on the blockchain. And is this is where things got really exciting in blockchain because now you're able to do, you're not just accounting for who owns what coins. You're accounting for which programs are being run and who is triggering those programs to run. And then now we also have the advent of Oracle networks, right? Now I can fetch information from outside of the blockchain and put it on the blockchain. Now, if the weather changes, I can use that as an input to my smart contract on the blockchain. And a smart contract basically is an automated enforcement mechanism based on conditions that aren't necessarily pre-existing. So I deploy a smart contract on the Ethereum blockchain, and anyone can call a function, given that it's a public function. Anyone can call a function on that smart contract and use the smart contract, right? So all of the tokens that we see on Ethereum, right? The Uni token, um, uh, I'm trying to think of some tokens that are high. It's not too many meme coins on Ethereum these days. It's mostly like RWAs and stuff like, Aave token, Go token. Oh yeah, of course, USDC, USDT. These are different tokens that are used to account for who owns what of that specific token. And the only way that that is possible, like that's not possible on Bitcoin because Bitcoin only accounts for Bitcoin. With smart contracts, you can deploy a token smart contract, and now you have a way to verify on the blockchain who owns what of that specific token, not of the Ethereum token, Ether.
Last, I want to cut you short. I want to ask you some questions.
Hmm?
Um, what is Bitcoin? Uh, and what is a smart contract? Did you explain a smart contract? Did I miss it maybe?
I tried. Let
Okay,
let
so
me
maybe explain what Bitcoin is and then explain what. So when you say Bitcoin and you say Bitcoin network,
mm.
and then when you say Ethereum and then you say smart contract, what are you talking about?
Yeah, so the Bitcoin network is the consensus mechanism that runs how the Bitcoin currency moves, right? So Bitcoin is actually a coin. It's a coin. It's an internet coin. But the network needs to determine who owns what of that coin because there are 21 million coins out there and all of those coins can be divisible almost infinitely, right? 18 decimal points. So the Bitcoin network is a group of people doing this puzzle over and over again to try to add new blocks to the blockchain and validate the updated state of the coin itself. And what I mean by the updated state of the coin itself means who owns what of the coin. That is the only job of the Bitcoin network, is to safely determine who owns what Bitcoin. And then for smart contracts, it's a little bit more sophisticated, right? It's not about who owns what of the coin, but what state, what programs are actually taking place on the blockchain, what programs are running on the blockchain, right? So a smart contract is USDC. USDC is a smart contract that accounts for who on the Ethereum blockchain owns USDC. So when you send those stable coins, you're sending that transaction to the USDC smart contract, right? When you have Uniswap governance tokens, that's a smart contract that determines this person who owns the Uniswap tokens can vote on this protocol, and they're also able to move their tokens around. You know, you have airdrops. An airdrop smart contract is a smart contract that takes a list of wallets and it sends tokens to those wallets automatically based on activities that they've done in the past.
Yeah, so let me just give some context. So remember when Lance started speaking, he spoke about some qualities of the internet that were not so pleasing or not so efficient, right? So, for example, security is a big, it's a huge risk on the internet, and then, requiring trust, requiring that you need someone to, you know, basically verify on your behalf. For example, like a bank, you need a bank to prove that, you've got this X amount of balance in your account. So there's all these qualities that led to, that have been, people have been trying to figure out how can we basically build a better internet, and some of the ways of doing that is what Lance had covered around cryptography, some tools, some of the earlier tools. Now, Bitcoin was one of the first use cases where uh, the builders of Bitcoin basically created a network that could verify all these transactions, or could help, I guess, the participants achieve consensus without necessarily having to know each other or trust each other. So that was the first kind of blockchain, as we call it,
Mhm.
as it were, which is now the Bitcoin network, right? And now, as amazing as that use case was, and as much as that served to prove that, okay, we can store this kind of data on the blockchain and it's verifiable by all these nodes, there was still the need for internet infrastructure that had all these qualities, but then that we can build on top of. Now, the Bitcoin network only had one use case, and the use case of that is just proving the state of the Bitcoin. And every time you do that, uh, you basically earn a Bitcoin. So these people who are running these nodes, so you know how like the internet has AWS and Google and all this server infrastructure. The only way blockchains work is if now people come together and then contribute those resources to sustain that network. And how you get rewarded for that work, for providing compute and memory and all these things, is that you earn these bitcoins. And so, yeah, so that was proved. You proved that, okay, we can actually sustain our own network with an inbuilt incentive, which is now the Bitcoin token. I mean, the Bitcoin. But then that itself was also not sufficient for builders, especially for people trying to build stuff on the internet or on chain. There's people who are looking to build on this new technology. And so that's now what necessitated um, what, you know, the programmable blockchain, such as Ethereum, which is the world computer, as Lance is mentioning. And so now he's getting into how that works, which is now through smart contracts. And so all those rules that we said were like really good that kept the Bitcoin, network, I guess working. A lot of those rules can also be embedded in code, and that's kind of what smart contracts are. I would say maybe the smallest or the finest example of that, self-executing code, which I guess now Lance will continue. Sorry, Lance, for hijacking. I'm always fighting for the new guys. Yeah.
Yeah, yeah, no worries. It's necessary. Um, yeah, I mean like actually welcome to keep the discussion going. I think this is probably the most important slide, especially for Web3 clubs, because Web3 is mostly built on Ethereum and its primitives. Does anybody else have like
100%. Yeah.
anybody else have questions?
And there's no dumb question. And I know there's no way everyone here has completely understood what we've been discussing. So I really would be expecting you guys to be sincere with yourselves more than me. And yeah, I might just call out names actually, and catch some consensus over here. But yes, let's continue.
Okay, cool, cool. So so we have Ethereum, right? So then there were these researchers. Okay, I guess the first thing that we need to discuss is gas because um, let's say you do have a computer, a computation, a smart contract on the blockchain, right? How do I stop someone from running a smart contract over and over and over and over again and clogging the network, right? Because in order for the state of a program to update, then everybody else in the network, everybody else in the Ethereum network needs to update their computer as well, right? The Ethereum consensus network works a little bit differently from proof of work. It uses proof of stake, which is something that we can get deeper into if you want to. Just ask the question and we can explain it. But just overall, Ethereum doesn't run on proof of work, it runs on proof of stake, right? But what happens if I have a program on the Ethereum network and I have somebody that's just, being a malicious actor and running my program over and over again? So this is where we get gas. Every time you run a computation on the Ethereum blockchain, you have to pay for that compute. And the reason why you pay is because there are people who are using their computers to run these programs, and they need to pay for electricity, for maintenance, etc. Right? So it's a simple economic system where, I'm contributing to the network, I'm contributing compute to the network, and in exchange, I'm able to get paid. This is why people mine Ethereum, people mine Bitcoin. But then what happens if I'm not being egregious, like I'm not being evil, but I genuinely have a lot of computations to run on the Ethereum blockchain, right? Like, what if I want to, what if I want to have on the blockchain a state that, let's say, uh, I have a game. Let's say I have a game that I want to run on the blockchain. A game is an intense computation. It's an intense platform, right? You're not going to be able to run that directly on the blockchain. So this is where zero knowledge proofs came in to play. So a zero knowledge proof, you can think of it this way. It is a way to prove that something was done in a certain way without verifying any of the information underlying it, right? So, for example, let's say underneath my screen, I have a number, right? You see the number 7 right here, but then once my hands leave the screen, I change the number. how do any of you know the number, right? How do I prove to someone who guesses the number right that they're actually correct? Because I'm the one with my fingers right here. I can change them last minute if you guess correctly, right? So it's a way for trust to be expanded beyond direct compute running on the blockchain to now being able to run anywhere. The compute can run on any computer, and a proof can be generated that that program was run correctly, right? So one of the most famous examples is of the Fibonacci sequence. The Fibonacci sequence is it starts with 1, 1, and 2, and then the next element in the sequence are the past two elements added together. So it starts with 1, 1, 2, and then you add 2 and 1, it's 3. You add 2 and 3, it's 5. You add 5 and 3, it's 8, and then so on and so forth, right? Let's say I wanted to take a number and prove that it is a part of the Fibonacci sequence. What I would have to do if I wanted to run that on Ethereum, I would have to run the Fibonacci sequence all the way from 112 way back, way up to where that number is supposed to be, and then verify that it's equal to that element in the Fibonacci sequence. That's going to cost me a lot of gas. So then what I do instead is that I create a script, maybe in Circom or Halo 2, which is one of the zero knowledge proof languages, and then I use as a witness, I say, hey, this is the number that I'm showing you. It's the public input to my zero knowledge proof. It's the element that I want to prove is inside of the Fibonacci sequence. And then there's a verifier smart contract on chain that says, okay, cool. If you give me a valid proof that this element is in the Fibonacci sequence, then mathematically I'll be able to verify that. Now, the math underneath a zero knowledge proof is extremely complex, and it is worth kind of dividing them into their big primitives, which is a snark and a stark. So, a snark is a succinct, non-interactive argument of knowledge, and a stark is a succinct, transparent argument of knowledge. So, in a snark, the N represents non-interactive, meaning that if I have a proof, then I can send you this proof, and that's it. I have no interaction with you. It's one directional. A Stark is transparent, meaning that there is actually a little bit of interaction that has to be done between the prover and the verifier in order to verify the proof. It has to go, one way and another. It's transparent between the parties. The benefits of snarks is that they're much smaller. They consume less compute. The benefits of Starks is that even though they're larger, they can prove huge amounts of compute, right? So the Fibonacci sequence, for example, is what you would use a snark for because it's a pretty small computation. All you're doing is proving that you've added two numbers together in a sequence. It's just summation. Whereas a Stark, if you want to prove, for example, a virtual machine, which is an actual computer, as in, I want to prove that my MacBook is running correctly, that's when you would use a Stark because you're using multiplications, you're using moduluses, you're using divisions, you're using all these complex operations. That's when you would want to use a Stark. And a Stark typically is proven over a few rounds of interaction. So some of the popular ZK VMs out there are like RISC-0, SP1, Jolt. There's this call for the Ethereum uh uh proof. Oh man, what was that called again? Um Sorry. So I'm forgetting the name of the monthly Ethereum call, but it's basically a monthly Ethereum call to prove or to see who has the fastest ZK VM. Oh yeah, it's called ETH proofs. Sorry. So basically, Ethereum is moving toward the direction of the ZK VM because imagine if you didn't have to learn Solidity in order to write a smart contract. Imagine if you could come to Ethereum with any programming language that you know and then create a verifiable blockchain-based program that you can get blockchain-based security with it. So, for example, that game example that we had brought up before. If I want to run a game on the blockchain, I want all of my game assets to be tradable with people on the network. I want all of my um, game state to be consistent across anyone who decides to join the game, and I want to do it based on blockchain, then it would be in my best interest to use a ZKVM because the ZKVM can prove the state of the game to the blockchain without necessarily running the entire game on the blockchain itself. So you're not paying millions of dollars in gas. You're just paying a few cents in gas every, few minutes or so, and you're just proving the state of the game over and over again on the blockchain. So this is really the direction that Ethereum is going. Even Vitalik has said over the next like 5 years, Solidity will be optional to write smart contracts. You'll be able to write smart contracts in any languages. One thing that I didn't mention on this just yet are the L2s on top of Ethereum. So though the L2s are different blockchains that are used to help Ethereum scale and make transactions cheaper, right? So let's go all the way back to Merkle trees. This is the fundamental concept of how an L2 works, right? If I have four transactions on a layer two blockchain, I can basically condense them into one transaction and then just prove that transaction on Ethereum whenever someone comes to challenge it. So that's the basics of how an L2 works. And there are L2s that are thinking about running fully on ZKVMs. So, for example, Optimism, I think Base as well has been floating around the idea of running their L2 on a ZKVM so that, oh yeah, and then also Arbitrum, they've been working actively toward running ZKVM in order to expand the capabilities of their blockchain while still maintaining the security of verifying all computations on Ethereum. So that's the end of my presentation. Just going back to the the call to action is that this is still being put together, right? This is not a finished product. The earliest concept that we discussed in this presentation was from 1976, right? And with AI, you can essentially teach yourself in depth, like PhD level, any of these subjects because all of the papers are out there on the internet. It's just a matter of going about learning them in depth. So the world is your oyster. Congratulations, cohort 10, and welcome to Web3 clubs.
Yay! Thank you so much, Lance, for the session. I feel like you took us on a journey, and I'm very excited to know or to get some of the sentiments from the guys in the audience, especially those who haven't interacted much with blockchain before. So it doesn't have to be a question. Sometimes, Lance, when when you go too deep, sometimes people don't have the time to digest it. I can see guys asking for slides, and we're gonna go in depth with the uh, sessions that we're gonna have later on. So right now, feel free to just share your thoughts on the session. Yeah.
Yeah, I'm actually looking at this reply from CK. Really good intuition on how the UTXO model works.
Yeah, guys. So Lance really dived deep there. We might even pull it back again in the other sessions. It's really the whole process about understanding like blockchains and Web3 and all that. It takes time, and that's why we even give it a whole week. Um, we might even make some of the sessions maybe just more engaging, like have guys have conversations with each other and get back at us. Because it's not good to assume that, okay, this session is done. Boom, everyone is good. Let's go to the next one. It will take time. Please do not feel like, oh God, I didn't get that. Am I not smart enough? Oh my God. Like, do not find yourself in that space. I know in this first session is someone is thinking, looks like I'm not going to make it to the end, of this cohort. Do not do not think that. You literally do not even have to fully get some of these things now necessarily. Remember the cohort is about building on chain using AI. Using AI to build is super, super simple. Uh, Maybe even simpler than these foundational ideas that we're sharing now. So please just hang in there. I promise you, after after week 3, after the end of week 3, latest end of week 2, week 3, like you would be super comfortable. Please do not be a dropout on an online school. Yeah. So like online school is the easiest. All right. Yeah, I think that's it from me. Washuka?
So
No,
I,
I think, yeah, go on, Lance.
I was just gonna say I put my Telegram in the chat if y'all want to reach out, and then maybe I could share the slides in the WhatsApp chat for everyone.
Yeah, that would
Yes.
be dope.
Okay,
Lance is in
cool.
the group, guys, so please just ping him. Just tag him, ask questions. Yeah, there's someone has raised their hands. Let's see.
Everyone.
Yes, go for it.
Yeah, so I deeply apologize. I feel I'll have to take you guys way back to almost the start of everything. Yeah, so okay, I have knowledge on Bitcoin, Ethereum, the ecosystem, and all that. I know later on we'll know the relationship between the Bitcoins and now the other currency like the TRC20 that we have on the network. So I have very little knowledge on cryptocurrency as a whole ecosystem. Yeah. So my question is like, uh, when getting into this Web3 club, like how much knowledge does someone need to have? Do we need to have like coding knowledge or knowledge on any kind of cryptocurrency ecosystem, or what kind of knowledge do I need to come with to this? Yeah, I hope my question is relevant.
Yeah, so you need to come into this, you're coming into this seeking knowledge, so you don't really need to have so much prior knowledge. We start all these programs with very fundamental, foundational theory and just basically just I'm covering like the basics. So no, not really. Also, this cohort has also been built for the non-technical founders. So for those who may feel like, oh my God, what's going on? Um, there's a part in this cohort where, and this is foundational still. This is still theory. Um, so no, you don't even have to be technical, honestly. You really just have to be passionate about building problems. I mean, building solutions for problems. Most of us here are building in tech, so that is a plus. But no, like you just come as you are. Is the short answer for
Okay, thank
anyone
you.
there who's feeling like, oh, no, there's no real like crazy barrier. Yeah.
Yeah, okay.
There's another question from Devi. Hi, Devi. Good to see you here. You're asking what blockchain skills should one focus on learning in 2026 to remain relevant? I think, Lance, you can pick that up after, maybe what's your experience you've been in the industry for a minute now. What's your observation over time on what it takes to actually be relevant? Should we understand everything like by next week for you to, yeah.
Yeah, so there's this one example that I always look back at. Um, there was an individual who worked at Nethermind. And for those not familiar, Nethermind is a blockchain development, security, very, very generalist company. They are the ones behind a couple of the Ethereum consensus and execution clients that are run to run the blockchain, as well as they have a really good auditing firm. So they're overall like a really well-known, high-profile company in the space. And they have a person there whose entire job is to work on anything related to compilers. And essentially, what a compiler is a program that translates human readable code to machine code. But David, what you would ask is what blockchain skills? I would kind of tweak that to what blockchain skill, because in the age of AI, right, being broad is not an advantage. It's best to be a complete dominant expert at a really specific thing, not just blockchain, right? Maybe you're specifically good at, automated market makers, or you're really good at the smart contracts behind derivatives protocols, or you're really good at specific types of ZK proofs. If you can be top five globally in just one of these small fields, you'll end up having a lot of outsized value in your career. So for me, before I started Sereel, I had spent a couple years freelancing for different companies. And what I did is that I combined my knowledge of AI and tensor networks with ZK, and I spent a lot of time in the ZKML industry. So I worked for two of the biggest companies in that specific industry of creating zero knowledge proofs for artificial intelligence models. There was probably a total of 200, 300 people in that entire industry, right? It's better for me to compete in an industry of 300 people versus being a generic Solidity engineer where there might be 30,000 people, right? So being really good at really specific things is what's gonna make people prosper in the age of AI. You should really think cross-border when working in Web3. The world is your oyster. But yeah, I would, I mean, specific skills, as I had said, ZK VMs. So maybe if you do an overview of the different ZK VMs, I know that there are some ZK VMs that are completely run on these things called lookup tables. And if you get really good at those, guess what? You can probably approach some of the ZKVM companies with your skills, because a lot of these AIs can't even do a lot of the ZK programmable cryptography, the FAT that a human can just yet. So yeah, like if you aren't a founder, if you aren't building a company, right? It's different if you're building a company. If you're an engineer, specialty is key. But if you're creating a company, then it's strategy. It's not about specializing in one technology. Maybe if that company relies on the technology, but it's about strategy. And then CK, what if the domain gets obsolete? So obsolescence is what happens when people no longer find utility in a technology, right? What happens is that the only time a technology really becomes obsolete is when it stops finding use cases. So throughout the presentation, right, we're looking at these technologies that had come out in the 70s, the 80s. They didn't have use cases for 20, 30 years. It doesn't mean that they were necessarily obsolete. It's just that they lacked a proper use case. So if you are specializing in a technology and the market isn't necessarily, paying attention to it, that doesn't really mean that it's obsolete. It means that people just aren't paying attention to it, because let's be honest, the people, most of the people in the Web3 space are going to be chasing most of the hype, right? What's the next hype cycle? It's not necessarily about, okay, how can this tool really be used to solve a really core problem? And that's where you need to have a I think everyone should have a mind for entrepreneurship because if you specialize in a technology and you know all of the use cases of that technology, then it's just a matter of time until you come up with a new use case that people haven't thought of before. And now you capitalize on that new application, right? Prime example is the zero knowledge proof, right? Zero knowledge proofs were first thought of in the 1980s. It wasn't until expensive blockchains came around where someone who was old as hell came up with or like just connected zero knowledge proofs to saving compute on blockchains. Someone who had just so happened to already study zero knowledge proofs, which were at that time considered obsolete, but then they applied it to blockchain, and now it's a multi-hundred million dollar industry, right? So because you specialize in something, take pride in that. But if people aren't paying attention to it, it doesn't mean that it's obsolete. It means that you probably have an opportunity to create something new that people haven't been thinking of before. I hope that helps, CK.
Yeah, thank you so much, Lance, for that. Any more questions? We have like 15 more minutes that Lance had allocated for the Q&A. Any other person with the courage to speak up? I feel like it would be a good time to also throw a stupid question and ask, what is Bitcoin? You know, again, maybe now you have questions. You know, if we go deeper.
Hello,
Hi, Gabriel.
I'm Gabriel Nyamu. I have a question about the tokens that I think I'm not are there, but people don't know about them. I'm not sure. But so it is mostly about ERC 8004.
I'm actually not familiar. Which one is that?
It's a token by Ethereum called ERC 8004.
Oh, the agent standard. Yeah, this is where
Yes.
like it's some type of agent metadata. I haven't really looked into this one too deeply. Can you enlighten me?
I wanted to know how it works, if it's basically just like the normal tokens or because I know it's basically made for agents and the identity about agents. I wanted to inquire more about it.
Yeah, I'm the wrong person to ask about that. I have not looked into this. I see that they do have ZKML proofs as a part of, and also TEE oracles as a part of the trust model. Um, I haven't worked in agents in a while. It looks like this one was August 2025. So that was a little bit after my heyday. But hey, Gabriel, if you're interested in it,
Yes.
this like read through the are you looking at the EIP like this link right here? Read through it, implement it over and over again, tweet about it, make blog posts about it, make yourself an expert,
Okay. Okay. Thank you
and
for.
then teach me about it.
Yeah,
Okay.
so it's ERC what again? It's ERC?
8004.
Yeah, so we do have a trainer who does specialize in this, or
Wonderful.
basically someone who will be walking guys through agents for Web3. So yeah, protocols for that. So Gabriel, that um that question will be addressed. Uh, I believe around maybe week 4 or 5 there, but I don't know. But I'll add one of the trainers into this group, and they may be able to address this earlier, much earlier. Yeah.
Yeah, and Chris, that also might answer your question around AI agent frameworks. I know there's like X402, there's there's these like agent orchestration networks. I'm like, it's a lot out there. Thanks, Dennis.
Yeah, there's
Yeah,
a
no.
lot. There's some guys I'm talking to who I'm creating an agent marketplace, I believe, where you can trade skills, can even trade those agents. So I hope that really goes well, the conversation we're having. But yeah, they may be able to give a session or two on that.
That'll be awesome. I actually wanted to talk Halivis. Can you elaborate on this question that you posted around how do government intelligence get to free assets on chain without involving the nodes?
Yeah, Levis, maybe you can even unmute and just explain your question, maybe clearer, or you can, yeah.
What I was trying to say is freeze assets.
Mm. Well, when it comes to freezing, Tether and Circle were able to do that from the jump. It's just a function in the smart contract, right? They have a wallet that has authorization to do that. And then
Okay.
yeah, like when it comes to the effect of stable coins and crypto becoming mainstream, there's a lot more, I want to say, responsibility on the issuers of these tokens. Because imagine if you lost $3 million in a smart contract exploit, and you have the ability to call up a government to transfer that money back. Will you take that opportunity?
Yeah.
Yeah, you know, you just got to expect human beings to be human beings. But it doesn't necessarily mean that your funds aren't safe because I mean they've put statements out saying that this is only for law enforcement purposes, etc. But it is kind of, sobering to know that if they wanted to, they could move your funds, which is why this project isn't done yet, because that's actually a problem. That could be a whole startup of like, how do I ensure that my stablecoins are safe from USDC and USDT? How do I preserve that value without necessarily having those stablecoins in my wallet? Yes, Joy Lisa is right. Bitcoin currently has a lot of quantum proofing efforts going on. I think there was like these new quantum computers. I think you need 1,000 qubits to function together in order to break ECDSA, which is what Bitcoin and Ethereum are running on. And right now they've gotten to like 100, or it could be like 10 and 100. It's some type of order of magnitude, but they're getting close on the quantum race. Um, yeah, David, the biggest security threats facing blockchain networks today actually is the quantum threat. There could be a breakthrough in the next year that makes quantum computers um, able to solve for Schnorr and ECDSA signatures. The thing is that uh, there is not only active efforts on the Bitcoin community, but then there's also a way for Ethereum. I think Ethereum has this like emergency plan. I do my best to keep up on the Ethereum all core devs calls, but I think they've been coming up with a real solid plan that in the event that there is a breakthrough in quantum computing that could break these signatures, there's like some type of ZK snark that you can, or Stark that you can add on top of everyone's Ethereum wallets that it would essentially prove that this person owns said wallet, and it would require the proof along with the signature to actually process a transaction. And as we had said in the presentation, ZK Starks are quantum proof. And the reason why they're quantum proof is because they don't rely on the complexity of ECDSA. They use Reed-Solomon codes, which have another order of magnitude of complexity to them. My thoughts on fully homomorphic encryption, it needs to get done as fast as possible because it's lattice based. It's also quantum proof, but then also it enables us to train AI on encrypted data, which is something that we needed yesterday because Anthropic is about to IPO and all of our Claude data is encrypted, but they need to decrypt it in order to train their models. So it kind of defeats the whole purpose of them encrypting it in the first place. Can blockchain ever be completely secure, or is secure always evolving? That's up to you, bro. Lot of people think that Ethereum is perfectly secure. But if you find if you're able to prove that's wrong, the only thing that's right in this world is what's right. If that makes sense.
Yeah, that's very interesting. Hmm.
I don't think anything can be
True.
completely secure.
Hmm.
Washuka, you're muted.
Yeah, oh yeah. So thank you so much, Lance. So I've noticed I can't open the slides that you sent in the group.
Yeah. Let me try to convert those to PPTX.
Okay. So I'd really encourage you guys to go through the slides, read further on your own, ask Lance questions in the group, because it might go deep really fast from here. Demo day is only 2 months away, and yeah, so the quicker we get this stuff, the better, and you have all the support that you need to get started. So I think we can wrap it up if we don't have any more questions,
Lance,
right?
no assignments?
Oh,
Yeah, this is cool, man.
oh,
Just,
you
nothing too crazy. Just.
all right. Implement an EIP of your choosing in Solidity. Mm.
Wait,
So
wait,
so
hold
so
on. Calm
Gabriel.
down. Calm down. No, actually, yeah, why not? Just
Yeah,
put it in the group.
yeah.
Uh, okay, look, those who struggle with this is not by any means like, you know, I mean, Lance, I think that was a bit unfair. I thought it was gonna be something more like, I don't know.
I mean,
You can't
I
introduce
mean,
blockchain day one and then ask guys to write a smart something on Solidity. I don't think that's fair, man. I have to
Hey,
stand with the people on
LLMs
this
are
one.
allowed, huh?
Yes, 100%, 100%. Yes, go for it, go for it. Uh, what do you want guys to do? Just put it in the group,
Oh, in the WhatsApp group. Okay, yeah, yeah. And
in the
Gabriel, I'm
WhatsApp
gonna
group.
be looking for that implementation in A004, specifically that one.
yeah, I think it's gonna be cool, just figure out what that is, and then if you have any questions,
Yeah,
Lance has shared his Telegram, just go as
yeah,
intense as you
yeah.
can.
Google it or Gemini it or Claude it. Like
Use
if
an
there's one
agent.
word, if there's one word in that sentence that you don't understand, like Claude it. This is basically AI world. Like this, do whatever. Yeah, this will be very interesting. I'd be so curious to see what the guys with non-technical backgrounds, like what they come up with.
Yeah, yeah. I want to see too.
Yeah. Alrighty.
All right.
What's
Yeah.
that? I think that's it. Cindy, Washuk.
Yeah, that's it. That's it. Thank you so much, Lance. Thank you guys for
Yeah,
joining
thank you
us.
all.
Tomorrow we are still here. We're back at it. Tomorrow, so Thursday and sorry, tomorrow is Wednesday. Wednesday and Thursday. We have sessions
Yeah.
back to back. So yeah, see
Yeah.
you guys. See you guys soon. Thank you so
Sweet.
much, Lance. Have a
See
great
ya.
night.
Good night.